Welcome to Breadboarding. This is video 40 in the Breadboard 8088 PC series, and in this video I'm going to be covering the first step of converting the floppy disk controller from using DMA to use programmed I/O. Now, if anyone's been following this, you'll be aware of I've been building out a basic floppy disk PC on solderless breadboards. Now, the middle phase here I've largely completed, although I did have some problems trying to run later versions of MS-DOS than MS-DOS or PC-DOS 2.10. Just because after a little bit of time the DMA controller seemed to be running into trouble. Now, I tried for many weeks to try and resolve this, so in the end I decided that perhaps what I could try and do is to remove DMA from the equation, and in one of the previous videos, which I'll include the links at the top and also down in the description below, I questioned whether or not having DMA at all was actually worth it. I think the summary was that it wasn't. So this is the diagram I put together to show what all the different steps that actually happen under floppy disk access to one floppy disk sector under DMA. So I won't go in detail about what's going on here. You can see the link in the top right hand corner of the screen here for the video I discussed this, or in the description below I'll include the links. But basically what was happening in all these steps, this covers both steps covered by the processor, the CPU, and also the DMA controller, the direct memory access controller. And to summarize, basically what happens is once the command has been sent to the floppy disk controller here, then in fact what the CPU does is just waits for an interrupt 6 to occur in a timer loop and goes round and round in circles whilst the DMA controller carries on actually reading data and writing it to RAM. So what I've done here is a slightly simpler diagram. So this is basically what using programmed I/O results in, and you'll see that there's quite a lot fewer steps here. I think the previous one was about 18 steps, and this one's I think about 11, of which there are a number of them which were shared anyway. So I think it probably reduces the number of steps necessary in the process by probably to about a third of the bit that does the DMA. So what we're doing here is once we send the read command to the floppy disk controller, under the DMA model, then what would happen is that the DMA controller and the floppy disk controller would talk to each other and sort out everything. However, because the CPU was just sat there doing nothing during this time, it wasn't really very useful. So what we're going to do now is that with programmed I/O, what we do is the CPU is going to check a status register in the floppy disk controller to check till it gets to a stage where it's actually got some data to read. Then the CPU reads the data from a floppy disk controller, then writes it to the appropriate bit of RAM, then increments the address, and then checks to see whether the floppy disk controller execution phase has completed. And basically the execution phase then leads into the results phase. Then if it has finished that, so after perhaps a sector or many sectors, it will go around in a sort of loop. So the floppy disk drive will carry on reading data, and then the CPU, as long as it can keep up and go fast enough, it will keep on checking the status register, and then every time there's some data it will then go through this process, and then it'll actually go back and start again. Now obviously when we get to the end of the execution phase, we've read all the data that the floppy disk has been asked to find, then we then read the results from the floppy disk controller, and then we complete the BIOS call. Now there's a few things we need to be aware of. Because the floppy disk controllers have been designed to work with the DMA controller, then there are certain signals it does expect. So the end of process signal or terminal count signal is something that the DMA controller uses to signal the floppy disk controller everything's finished. Now because that won't be occurring, then there are a few things we have to worry about a little bit later on to take care of that. So the main thing really here is there's no use of DMA or even the interrupt 6, which is the interrupt allocated to the floppy disk controller. So let's have a quick look at one of the block diagrams I've been using during the series, and what we're just going to look at here is this is the various parts: the microprocessor, all the bus buffers and latches, address decoding, the BIOS which sits in ROM, the memory, and the floppy disk controller. The solution we're going to be looking at the moment basically works with these components. What DMA required, and this is what we've covered over quite a number of videos, and it's really quite a complex process. So I'm just going to very briefly show you what all the different bits which are needed to allow the floppy disk controller to read and write directly to the RAM under the control of the DMA controller. So we've got the DMA controller itself. It needs some extra address latches because it doesn't have quite enough pins to do 16-bit addresses, and it also needs this page register to do the top A16 to A19, so it can do the full 1 megabyte address range. Then we've got various other programmable logic devices providing bus control signals, so we need to actually arbitrate between when the DMA controller accesses the bus and when the CPU accesses the bus, also making the CPU pause, so the DMA wait makes the processor sort of pause whilst the DMA controller is doing its stuff. Then there's some more IO PLDs, buffers that I ended up adding, lots of signals going around all over the place. And then the actual process itself, that the floppy disk controller, when set up to use DMA, has to request the DMA controller to go and do something. DMA controller gets control of the buses, and it sends a DAC2 request. Then the floppy disk controller then puts the data on the bus, and the DMA controller arranges the data then to be written into memory. So this is all very, very complicated. And then at the very end of the process, the end of process terminal count basically tells the floppy disk controller, we're done here. You've done everything you need to do, and everything completes. Basically, all this orange stuff here we can avoid needing to have if we manage to get this programmed I/O working. So I'm pretty sure that if I can get this working, then it will simplify things substantially. And about the only other thing I can ever remember needing DMA, there might be some network adapters that could actually use DMA for reading data into memory, but I'm pretty sure programmed I/O could also be used. Now, programmed I/O is theoretically not as fast as DMA in the original PCXT, just because they were using the basic sort of 5 megahertz versions of the 8088 processors. But as soon as we got to 286s and higher, then programmed I/O was generally going to be faster than legacy DMA. So it's pretty likely that for this design and future designs, then really the trade-off between not using the DMA controller is not really a very great one. And at the end of the day, the DMA controller, I think in one of the earlier videos we said could do about 400 to 500 kilobytes per second. Now the floppy disk drive would never be able to read data at that sort of speed, so it's really irrelevant really from this point of view. So in the previous video I mentioned that the IBM PC Jr didn't use DMA, so it didn't have a DMA controller and it used programmed I/O for the floppy disk access. Now there does happen to be a PC Jr technical guide, and it has a full detailed BIOS listing. So this is the part of the PC Jr technical guide which includes the full listing of the BIOS, and this is the bit in fact that has the read-write operations, and in fact there's a bit down here we'll be looking at a bit more detail that basically these loops here actually replace all the complexity that I was showing you on the first sort of block diagram, the 18 blocks, and this loop here basically does the read the data from the floppy disk controller when it's ready, write it to RAM, and then go back for the next byte until such time as you finished, and that's it really. So when I looked at this and saw this, I thought, wow, this is so much simpler than what DMA is. So that's what I'm going to try and do in this video, is take you through some of the things I've been doing, and I've now written the updates to the BIOS. We're not probably going to have time to test it in this video. I'll do a second video in a number of days or a week or so where we'll go through test it, and hopefully that will allow us to run later versions of MS-DOS like DOS 3.3, 4, 5 and even 6.2.2. And the PC Jr BIOS source has also been reverse engineered by Ricardo Quesada. Now this site here in GitHub is where all these things come from, so you can actually download the PC Jr BIOS listing. So this is actually a bit more searchable, a bit easier to use than the PDF versions of the IBM documentation. So this is the site, and you can see there's quite a few of the machines here. So we've got the PC Jr. The Tandy 1000 also didn't have a DMA controller, but I think they just copied what the PC Jr was doing. And the PC Jr, you can see here that we've got the details of the BIOS and also the listing that I'm going to be showing you. So this is the listing of the PC Jr, and the key thing really here is that the disk access routine, so this is the interrupt 13 main sort of procedure. I'm not going to go through this in great detail, but basically there's a disk read, disk format, and I think disk write bits, which then call the bulk of all the code uses this RW operation. And this is the thing in this particular BIOS does an awful lot of stuff. Now there's a lot of stuff here to do with turning on motors and doing things like that that we don't need to worry about, but the key thing we're going to be looking at is when we actually get to the reading and writing the data, then these loops here, the verify loop, the read loop and the write loop, basically replace all of the DMA stuff that we've been struggling with. And The other thing, one other issue about this is that because interrupts are disabled during this, then there are some issues to do with the system timer interrupts, and I'll talk about that as we go through, but I don't think we need to worry about that since we've already added a real-time clock. So the XI8088 BIOS has a number of procedures to do with the configuring DMA for floppy disk access. So a number of routines here, and this read, write, verify common code is similar to these things here. So in actual fact, these three here all use the same routine. So we can actually retrofit this relatively easily, and in fact the format track I think I've also been able to accommodate in this way. We're going to be disabling the DMA in the floppy disk controller and also the use of interrupts in the floppy disk controller. So some data operation register bits we need to worry about. And because we're not using interrupts, then a lot of the BIOS code has this floppy disk controller wait for interrupt, and we're going to have to replace that. And in fact, there's a check stat 2 from the PCJr BIOS, and that's a routine that polls these statuses and things and waits until the disk controller has actually got data available. So this is just looking at the original PCXT floppy disk controller, and I just wanted to highlight a few things. So when we look at the PCJr one, you'll see there's a few differences. So the digital control port, digital operations output port, this allows us to control up to 4 floppy disk drives, and when we then look at the PCJr, you can see that this is much simpler. It only actually has one drive, so motor on and select, but also it doesn't, because it doesn't have all the DMA stuff, what it does require is some control logic here. It's actually called a watchdog timer that basically, when it's doing operations, if was a failure in the floppy disk controller, it sets this sort of 3-second watchdog timer to set an interrupt on interrupt 6 if there was actually a failure, which means it no longer responds. Now, I'm not going to bother with this for the moment, because at the end of the day, if the thing fails at the moment, I'm just going to turn it off and turn it back on again. But this might be something we would need to add in future versions to put the watchdog timer in here. So I've simplified it a bit by not doing this, but we'll see whether or not it's necessary. Now, one of the other things I did come across is the floppy disk control that we're using, the Western Digital 37C65. The datasheet is wrong, and it's only really when I was getting down into the details of working out all the status values and things that I actually realised what was going on. So if we look at the datasheet, you can actually see here that basically the tables and things here and the references here are incorrect. And in fact, this first table here says it's status register 0. So the status register 0, 1, 2 and 3 are basically returned in the results once the floppy disk operation is completed. The master status register is available to be polled the whole time, and this is quite often what we're needing to poll when we're not using DMA, to see whether or not the floppy disk controller is ready or has finished or whatever. So the fact that this information was incorrect, and you see here that I've actually annotated this, that this is the master status register, not 0, and if you actually go through, you can see that all of the register numbers are incorrect. Now, it probably doesn't make too much difference to anybody when they're just doing the hardware, but as soon as you start to write the software, it gets very confusing when people refer to completely the wrong bits in the documentation. So I've updated this version. I will upload this onto GitHub eventually with the corrections on here, but it's something worthwhile. If anyone's looking at this, make sure that you annotate the register values here, otherwise you're in for a confusing time. And what I have done is actually also downloaded the IBM diskette drive adapter manual, and I include all the links for these in the description below. And this is where we obviously got the diagram from, but also what I've then done is compared all the various tables. So you can see that is the main status register, and then as we go through, there's command summaries, and then we've got the status register 0, 1, 2 and 3. So what I did is, after having found this out, what I have done is actually gone through and compared. On the left hand side here, we've got the original IBM diskette controller. So this was the one from the original PCXT, and over here we've got the one from our datasheet here. And what I have done, red highlights where it's incorrect, and orange just shows where there's a bit of a difference. So for example, the non-DMA mode here is known as execution mode over here, but it means the same thing. Basically, when we've turned DMA off, then this execution mode tells us whether or not the floppy disk controller is still executing a request or whether it's gone into results mode, but that's not incorrect, it's just slight difference in terminology. So when we look at 0, then again there's no real differences here, so the information is correct, it's just the reference and the table references are incorrect. Similarly for command register 1 and for 2, and then for 3 there's a few little differences, probably because this was done probably 10 years after this one. So the write protect versus two side, I guess two side became the norm, so you probably didn't need this in later versions. So there are a few minor differences, but it's definitely worthwhile checking back on the original IBM documentation whenever you find any discrepancies, just to see if anything's inconsistent. Now there are some differences because of the way how the standard PC versus the PC Junior floppy disk controller. If we look at the DOR register, the operation register, then in fact we can see that on the PC Junior on the right hand side we just have one drive enable, and then it has 2 lines for the watchdog timer, which we don't have on the other side, and then there's a reset, whereas over here we have 2 bits for selecting 0 to 3, the drive ABCD, and we also have the reset signal and the enable interrupts and DMA requests. So this is something we need to be aware of when looking at the code, because the data that's written to the operation register is not the same. So normally the PC initializes the operation register with 0C, which basically means bits 3 and 2 are set. That enables interrupts and DMA and means not reset, so reset is actually active low. Now going forward we need to change this to just 4, so we just want the reset to be set to 1 so that we disable DMA and interrupts. The PC Junior also has an active low reset, although it doesn't say that in the thing there. In the code of the PC Junior, when 8.0 turns the motor off and 8.1 turns the motor on, for example, is a common thing we see lots of. And then the 3-second watchdog timer, when these enables and triggers are actually strobed in the appropriate way, then that basically just means that if floppy disk controller hangs after 3 seconds, then there will be a process to actually recover it. Now in the DOR, the drive operation register, the 2 things we need to worry about here, we've just been looking at the soft reset and the DMA enable. So we're going to be making sure that this one is set to 0. Now the way how the PC Junior BIOS actually checks to see what the status of the drive is there is a command 8 sent interrupt status, and this is the summary information from the datasheet. Basically when we send this command, so it's 8, so that's 1000, which is 8, and then we get back the status 0, and we also get the present cylinder coming back. So this is the current cylinder or track that the floppy disk is on, and we can see over here this is actually status register 0, not 1, which is why it was confusing when I was first looking at this. So when the floppy disk controller moves from execution mode to results mode, then bits 7 and 6 indicate successful completion. If they're both 0, then it's success. Generally if 6 is the 1, then there's actually a problem there. And we also need to worry about the execution mode. So the execution mode in the status register is how we tell whether or not the floppy disk controller is still in progress or whether it's actually finished doing the current operation. So we'll be polling that execution mode quite a lot in the BIOS changes. There's also some other things. So the specify command is actually used to initialize the floppy disk controller with the head load time, step load time, and the head unload time. So the various parameters specific to each floppy disk drive. So if you had different types of floppy disk drive on a PC, then these would vary by the type of drive. One of the key things here is the bit 0 there, D0, is the no DMA or no non-DMA bit. Now that's normally 0. So the choice of DMA or non-DMA is made by the ND bit. When the bit is high, the non-DMA mode is selected. When the bit is 0, DMA. Now all PCs will generally have this initialized to 0, but in this particular case we're going to set this to 1 to actually disable DMA. Now the disk parameters are defined in the BIOS, but what we're going to do, rather than changing the defaults that are then written to floppy disks during formatting and things, we're going to actually intercept the value when we're going to send it out to the floppy disk drive, and we'll just set that bit. So in the PC Junior the value is 3, but on the standard BIOSes it will always be 2. And then the boot sectors have the BIOS parameter block. So whenever we format a floppy disk, then there is an area at the beginning of the floppy disk with the boot sector where again this specify byte is in there. So that's 02 for both PC-DOS 2 and MS-DOS 3.3. So we need to allow for this in the BIOS. So what we're going to do is, rather than changing all the floppy disks and things, we're just going to set the value to have 1 enabled when we've actually read the data in. I'm not going to cover too much on here, but basically this FDC wait IRQ is the main routine that basically causes the current default BIOS just to spin in a loop waiting for the floppy disk to complete. So as you can see, under real mode applications, DOS and things like that, then basically the processor doesn't do anything until such time as the floppy disk controller is finished. Under protected mode applications, under perhaps Windows 95, things like that, upwards, and Linux, and obviously it might be able to go off and do other things, but not in the DOS world that we're waiting for at the moment. And the key thing really is in the PCJr BIOS there is a checkstat2, which is actually used in almost replacement of this wait IRQ. So we're going to be going through and making changes and basically commenting out the FDC wait, and we'll replace it with this. And this uses the interrupt status command 08, which we were looking at a few slides ago. Then looking at the floppy disk controller datasheet again, we can see here that terminal count, programmed IO will cause abnormal termination error at the completion of the command when not in DMA host mode. So this sort of abnormal termination error we do expect when running in not DMA mode. And also the interrupt will actually be disabled anyway when we set the pin appropriately in the operations register. And so another bits here. When the controller is in the non-DMA mode, then the receipt of each data byte is indicated by an interrupt signal on pin 16. Now we're not using interrupts, but what it does say is that you may then poll the main status register and bit 7 functions as the interrupt signal. If a write command is in progress, the write signal forms a reset to the interrupt signal. So basically, because interrupts are disabled, we're just going to be polling status registers. And then another bit here, which is talking about this, but note that in the PCAT usage, non-DMA host transfers are not normal procedure. Controller will successfully complete commands, but will always give this abnormal termination error since TC is qualified by an inactive DAC. So because we're not using the DMA controller, then we have to handle this particular error. Now it just so happens that the PCJr code handles all of this and basically does the determination if it's completed successfully by comparing the requested number of sectors and the read number of sectors. And if those number of sectors are equal, then it knows that it was actually correct. Otherwise it would flag an error. So let's have a quick look at the changes in the code. So this is kind of a little plan I did. So I'd gone through the main changes are just done to the 2 floppy 1 ink, floppy 2 ink. These are parts of the XI8088 BIOS. And so basically I've identified all of the changes need to be done, and you'll see by line number and the various things we're doing here. And all these have now been done. And if you now have a look at WinMerge, I can show you the changes. So this is basically just comparing the default BIOS that I've been using up till now, modified for the Breadboard PC, with the PIO version. Now there are a few changes in these other things, but that's down to some other work I've been doing on getting disk controllers working. But the main changes we need to worry about are in the floppy disk 1, and you can see it's been updated on the right hand side here to use programmed IO. We've got the execution mode, although it's the same as stat DMA, I thought it was a little confusing to reference DMA, status DMA. So execution mode has got the same value that we're checking for in the bits there. Now the send specify, this is the bit I was saying that we need to always set bit 1 to disable DMA. So because when we send the specify command out to the floppy disk controller, then we're always going to set this byte, so we don't have to worry about doing it anywhere else. So this is the other changes. So we've got the floppy disk wait interrupt. This has now been replaced with this checkstat2, which is the routine that I was saying that come from the PCJr BIOS, and this exists in a number of areas. Then we've commented out the whole of the configure DMA. So by commenting all that out, then we've saved enough space so we don't run into any problems with addresses and things. And you can see here that now I've made a note that the floppy disk controller DOR now clears the DMA IRQ bit, and you can see here we're also not calling the interrupt routine. And this is the interrupt routine, which is now all commented out. And you can see here, this is the routine which is used to send data to the operations register. And we've now commented out the bit that always enables DMA. And now we're clearing bit 7 and bit 3, which is the DMA IRQ. So this basically means every time we write something to this, then we know that we've disabled DMA. So now we're getting to the changes. So this has come from the BIOS on the PC Junior. So I've used the various sources to actually update the comments here. This code here is polling the various values and things in the status registers and sending the sent interrupt status to the floppy disk controller, getting the results, and then actually doing loops to see what's going on. Then we've got some other routines. So bound setup, this is necessary that when we actually pass in the memory address that previously the DMA controller, ES and BX I think is the buffer where we actually want the data either to be written to from the floppy disk controller to memory, or whether we're going to write from the memory to the floppy disk controller. And what this basically just does is make sure that the extra segment actually has the majority of the address in it, and then the BX value is just going to be really the counter within a 64K page range. So this basically sets the variables which are then used by the string commands which are used to actually move the data between the floppy disk controller. But if we didn't done this, then we wouldn't have had the correct values in the index registers. So numtrans basically just calculates the number of sectors which have actually been loaded, and part of the success processing here compares the number that we requested to be read with the number actually read, and this is how it determines whether it's been successful. The read-write OPN includes a little bit of initialization stuff. A lot of the earlier code in the PC Junior BIOS wasn't required because we were already doing all that stuff with the standard XI88 BIOS. But there's a little bit here which determines which of the routines we're going to jump to. We do a little bit like disabling interrupts, calling our bound setup to establish what memory addresses we want. And then we've got the verify loop. So you can see here we're reading the master status register. Is the data ready? We read the data from the data port. Have we completed yet? If not, we carry around going in a loop. And when execution mode has finished, then we know that we're into results mode. And so then we can actually wait until such time as that is done. Now, in fact, the read loop, you'll see here that it's very similar. Verify basically just reads the data off the floppy disk but doesn't do anything with it. But this one, we can see that in fact this command here is actually store string byte. So this is actually the thing that actually writes the floppy disk data to the DI address here. It basically just goes around in that loop until such time as the execution phase is finished. Similarly with the write loop, the only difference here is that what we're actually doing is outputting the byte from memory to the floppy disk controller. This basically is a very, very simple loop, and the only thing really here is it needs to be fast enough such that the floppy disk controller doesn't have data waiting, which then can't buffer very much data in the floppy disk controller. So there is, if we can't do this fast enough, that we could run into problems losing data, so that's something we're going to have to check. And then at the end, basically, there's again a simplified process. We can call our standard BIOS get result routines, but the status information that we need to check is a little more complicated. So we're checking for normal termination, so these two values here should be 0. Otherwise we know that something is not completed successfully. And there's lots of comments here from the original BIOS, and then we're actually reading the various status values from the results and testing for all the various error conditions, CRC errors, DMA error, which we shouldn't have any DMA errors because we're not using it. If the sector's not found, address problems, format, and various other things. So this is very similar to what happens in the previous thing, but there's just a little bit more here to do with checking the number of sectors. So what this does is works out how many sectors did we actually transfer, and then down here we're actually doing a comparison, and on the basis of whether or not the requested number of sectors and the actual number of sectors is equal, then we're able to determine whether we set the carry flag and return with an error, or do we actually return the number of sectors in the AL register and the AH will normally have the error number if there was an error. That was the changes for that one. If we then just discard the changes there. So the bulk of the changes were actually in that file. And then if we come to this one, we can see here, we've just commented out the DMA, configure DMA. I've added a few comments here just because the read and write commands being sent to the floppy disk controller was slightly different between the PCJr and this one, but it wasn't an issue. Then this is where the largest changes are. So you can see now that a lot of what we're just doing, we just call this RW operation, so read write operation. A lot of the get result stuff we can comment out because this has been handled by that routine anyway. And if there was an error, then we'd basically just jump into the error handling routines a little bit further down. So in actual fact, the vast majority of the changes to the code were actually done in this RW operation. The actual changes needed to the rest of it were pretty minor. Other functions here, so this is the format routine. So again, this no longer uses DMA, calls the operation, and again we just had to comment out some of the get results and the get error because this is handled in this routine anyway. So just need to compile that, or assemble it should I say. You can see here that there are no actual errors, these are just the warnings where it's padding the bytes. So this is now actually assembled properly. So what I'm going to do in the next couple of days, I'm going to burn this into the BIOS. I'm going to see if this actually works at all. So hopefully I'll be able to boot PC DOS 2.10, and then we'll have a look and see whether or not we can actually boot later versions of DOS. So that will be DOS 3.3, DOS 4, and also DOS 5 and DOS 6. So thanks for watching. If you don't want to miss out on future videos, please hit subscribe. And if you found the content interesting, please hit like. It just helps to make the videos available to more people. Thanks for watching.